Welcome, Calculus AB. This is section 4-4, the Fundamental Theorem of Calculus. The essential question is, how are definite and indefinite integrals the same and different? Let's begin. So, Fundamental Theorem of Calculus. This shows the relationship between differentiables, which is chapter 3, and integrals, chapter 4 and beyond. The connection here, we've talked about it, and informally you can say that differentiation and integration are inverse operations, just the same way that division and multiplication are, or addition and subtraction are. So let's look at one way to illustrate that. On the left I have differentiation, so I had a curve here and I find the slope of a line, so we use it to find the slope of the line or the change of a line or slope of a tangent. Now, and slope of a tangent is basically saying like y over x. You have to divide, change of y or change of x. Well, with integrals, integration, you're actually finding the area of a region under the curve. So it's a little different. Now you're not finding the slope anymore, you're finding the area under the curve. How much is there? And one way to find area, especially if you're talking a rectangle shape, is change of y times the change of x. So there's that relationship similar to multiplying and dividing. Now the actual fundamental theorem is right here, and you're going to want to write this down. The function f of x dx integrated from a to b equals f of b minus f of a, where these capital F's are the antiderivative. So one way to say this is integrate f of x and then do the b minus the a. So here's another formal way to write that here. Let's actually do it. I have an example written out here. So I'm going to evaluate x cubed from integral of x cubed from 1 to 3. So if you integrate x cubed, get x to the 4th over 4. And the way we write that is I put this bar thing right here and write 3 to 1, just to remind myself I'm integrating from 3 to 1. So we'll plug in 3 first, which gets 3 to the 4th power over 4, minus 1 over, and then you're going to minus, plugging in 1 over 4, which becomes 81 over 4 minus 1 over 4, which is 80 over 4, which comes out to 20. Note, there is no c value, no plus c anymore, because this is definite integration. Since we come out with a number, we do not write plus c. It's not a formula or expression. It is a number. So let's actually do a few more. So I'm going to integrate this first one. It's going to be x cubed over 3 minus 3x from 2 to 1. And if I plug in 2 first, I'm going to get 2 cubed over 3 minus 3 times 2. Subtract and minus, plugging in 1, so 1 cubed over 3 minus 3 times 1. Okay, so let's simplify that. It's going to be 8 over 3 minus 6, and then we minus, this becomes 1 over 3 minus 9 over 3, which means minus negative 8 over 3, which becomes plus 8 over 3. Combining that, I have 16 thirds minus 6, which is the same thing as 18 thirds, which my final answer is negative 2 thirds. So there's my answer. All right, let's do the bottom one, part B. So if I integrate this, I get 3 times x to the 3/2 power times the reciprocal of the exponent, 2 thirds. And the 3 is going to end up canceling, so I get 2x to the 3/2 power, and we're integrating from 1 to 4. So if you plug in 4, 2 times 4 to the 3/2 power minus 2 times 1 to the 3/2 power. And I'm plugging in, so 4 to the 3/2 power, I'm going to square root 4 first to get 2, and then 2 cubed is 8. So I get 2 times 8 minus 1 to anything is 1, so minus 2. 16 minus 2 is going to be 14. Now let's use my T89 to verify this answer. So I'm going to hit second integral right here, and I'm going to plug in 3 times square root, second square root of x, close that off. X is my variable, and then you want to put the lower number first, 1, and then the upper number second, 4. Close it off, and my answer becomes 14, which is exactly what I got right here. All right, let's move on. Let's do one more. Now this is going to be with the trig function here. So integrate secant squared dx from 0 to pi over 4. So if you remember your trig identities, I think I do, that's going to be tangent of x from pi over 4 to 0. So it's going to be tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is going to be 1, and tangent of 0 is going to be y over x is minus, not equals, minus 0. So your answer is going to be 1. That's it. All right. Now the mean value theorem for integrals. We talked about the mean value theorem for derivatives. Basically, it says that if you have this function f, so a curve, then the integral is that somewhere between the part A and part B, there's some magical value f of c, so there's some c, where you can form a rectangle shape, and that's going to be the same area as integrating under the whole curve. So it's kind of like it's the value that finds the average of all that. So this curve right here, so basically this chunk would have gone into here. So let's see what that looks like. We have actually a formula for this. So the mean value theorem states if you're integrating f of x from a to b, it equals f of c, which is the c is what we're trying to find, times b minus a. And basically this is f of c is going to be your height here. So that's this height. And then times the length times height. And length would be b minus a, just like a rectangle. So we can rearrange the mean value theorem to find the average, because we might just actually want to find that average, and the way to write that is 1 over b minus a equals the integral of f of x from a to b. So I want to find that average. That tells me the average value of that y. Let's actually do this. I'm going to find the average value of f of x on the interval from 1 to 4. So using that formula, I go, this is going to be my a, this is my b. So 1 over b minus a, which is 4 minus 1, times the integral from 1 to 4 of 3x squared minus 2x dx. So integrate that. I get 1/3, so 4 minus 1 is 1/3, times, it's going to be 3x squared integrals x cubed minus x squared from 4 to 1. And if I plug that in, so I'm going to get 1/3 times, I'm just going to do everything together like this. It's going to be 4 cubed minus 4 squared. And then minus, you plug it in 1 cubed minus 1 squared. Alright, doing some math on this. 1/3 times 64 minus 16, and 1, that's going to be 0, so minus 0. 64 minus 16 is going to be 48 times 1/3, and it'll get an answer of 16. There's your answer. That's the average value. All right, moving on. So an example of this, and this is a visual representation of the graph. So the curve looks like this, the function looks like that, and from 1 to 4, my average value would form this rectangle shape. All right, second fundamental theorem of calculus. So another important part right here. And I'd write this down. If f is continuous on the open interval I containing a, then for every x in the interval, you have the derivative of the integral of f of t from a to x equals f of x. So notice the thing here. I don't have two numbers. A and b are not numbers. I have x at the top, a variable. And when you're taking the derivative of a definite integral of some function, basically you can just plug in this x for the function. All right? So let's see how this works in this example. So the derivative of square root of t squared plus 1 from 0 to x, that is just going to be plugging in x right here. So you go square root of x squared plus 1. Sweet. But we have to actually obey the chain rule for this too. So what if instead of having x, we have x cubed? Well, all you have to do is the same things before, but then times the derivative of this. So for this example, if I wanted to find f of x, I am going to use the chain rule right here. And so what's going to happen is, okay, so I'm going to use the chain rule right here, sorry. And this is going to come out to the plugging in x for here, we get cosine of x cubed times the derivative of 3x squared. And we'll do more of that in class. Now, we have something else called the net change rule. So you have this function right here. We've done this. We just did this. This was the fundamental theorem of calculus. The net change rule looks very similar, but instead of talking about f of x, we have f prime of x. So wait, why would we actually use something like this? Well, sometimes you actually have a rate of change of a problem. You're not just given the f function, you're given the rate of change of some function. So we can plug that in instead. Let's give an example of this. So in this example, a chemical flows into a storage tank at a rate of 180 plus 3t liters between 0 and 60 for t. Find the amount of chemical that flows into the tank during the first 20 minutes. So if we're going to do this problem right here, I can rewrite this, and this function right here, we're going to call this c prime of t, because it's a rate of flow right here. It's not, and our rate functions are going to be the first derivatives. That's 180 plus 3t. All right? So I know my c prime of t is that, and I want to actually find the amount of stuff that flows during that time. So I got to use that rate and integrate to find the amount of stuff. So I'm going to write this as from 0 to 20 is the time I want to go, and that this function right here, we're going to write 0 to 20 is c prime of t dt. And if we integrate that, that's going to be 0 to 20 of 180 plus 3t dt. So when you integrate that function, you get 180t plus 3t squared over 2 from 0 to 20. And let's plug in those values. So I'm going to plug in 20 for t. I get 180 times 20 plus 3 times 20 squared over 2. And then it'll be minus 0. When you plug in 0 for both of those terms, it's just going to come out to 0, so it doesn't matter. And doing the math on all that, you should get 4,200. And there's your answer. All right, that is it.